This assessment asks us to calculate the frequency of light that would be needed to excite an electron if a HOMO-LUMO gap is 142 kilojoules per mole. Our equation for this is here. It is lambda is the wavelength of light needed, and that is equal to Avogadro's number times Planck's constant times the speed of light divided by delta E, where delta E is the energy of the HOMO-LUMO gap. We need to know some things in order to use this equation. Delta E is given to us in the question. It's 142 kilojoules per mole is the HOMO-LUMO gap. Na is Avogadro's number, 6.02 times 10 to the 23rd per mole. H is Planck's constant, and C is the speed of light. We can use those values in this equation to calculate the wavelength of light that would be needed. So our wavelength of light is equal to Avogadro's number, 6.02 times 10 to the 23rd per mole. We're going to multiply that by Planck's constant. Planck's constant is given to us in joules. However, our delta E energy is in kilojoules, so we need to convert Planck's constant to kilojoules. That's a scaling of a factor of 10 to the third. So Planck's constant will use 6.626 times 10 to the negative 37th kilojoule seconds. The speed of light is given to us in meters per second, but our wavelength is typically recorded in nanometers, so we need to convert meters per second to nanometers per second. That's a scaling of a factor of 10 to the 9th. So we'll use 3.00 times 10 to the 17th meters per second, nanometers per second. And all of that will be divided by our delta E, which is what we're trying to, or our delta E is given to us. Our delta E is 142 kilojoules per mole. When we calculate this equation through, that will give us our lambda value, and our lambda value is equal to 842 nanometers. So we need approximately 840 nanometer light to excite an electron if the HOMO-LUMO gap is 142 kilojoules per mole. 842 nanometer light is in the infrared region, so we would need infrared light to excite this electron.